Okay, let's get started. So we were talking about the masked diffusion language model last time, and where we left off was the learned forward process. I'm sorry, the learned reverse process, which is given at some time t zt. Zt is now a vector of some masked tokens, some unmasked tokens. Remember the illustration? Zt is, let me see, where is this? Some cartoon somewhere. Yeah. So this is ZT. You go to T minus 1 is S. So this is ZS. Okay. Just recalling the notation because it's all a function of I, ZSI. This is T of I is I by T. S of I is I minus 1 by T. Okay. So this is ZT. And you want to figure out the next step. And this is what we derived last time. Okay. That P theta, the Lth took. So look at ZT is essentially the so you have a ZT given. The Lth token in that could either be masked or unmasked. If it is unmasked, then there's nothing to be done. Just carry it back one more step. You just keep it the same. And if it is masked, then because it's a masking model, this what you do is using the entire vector ZT, predict a soft token, which is a distribution over the vocabulary at time 0. And once you have that, remember that P theta is approximating the forwards posterior distribution. And therefore, all you say is that, well, it's equal to either mask with some probability or take the probabilities from this prediction. It's a soft prediction, and reweight that by the forward process parameters appropriately to say that, well, it could be any one of those with those probabilities. That's essentially the model. So it's just a categorical distribution over the alphabet, but augmented with a mask. Okay, this is where we left off. We did all this last time, and this is where we left off. Now the question is, how do you train this model? So the parameterization has pushed it to predicting this particular categorical distribution. Training this. Okay. So notation wise,
so that's that was one backward step.
Yes, this is one backward step.
It's either it has not denoised.
It has.
What I mean, so maybe I used the wrong word. I mean that it's a categorical distribution, as you're saying. So I have a whole distribution sitting on top of that token.
Right. Well, you could, but then you sample from that distribution. This is P theta. All we are saying is what is the back. Okay. So this is P theta. Now we've described what the P theta, what the distribution is of one previous step. Okay. Now how you decode what you actually get, how do you actually get an instance of ZT is a separate story. Okay. I'm not really even talking about it. You could do various things. While the default thing could be just unmask any token, okay, and according to this probability sample. There are many other things you could do, but all that I'm showing you here is how is the probability to be done.
And there's no let L on alpha S, so every token has an equal chance
no
to map into the categorical distribution. So this is when ZTL equals M.
This is ZTL equals M. Yes.
Right. So I have a chance. Yeah, that's perfect.
You're talking about this side or this side?
I have a 1 minus alpha S over 1 minus alpha T of staying masked.
Yes.
And that does not depend on L.
Exactly. But the mask is not.
With equal probability.
In this model, it is.
Will transition will become unmasked to this distribution.
Precisely. At least the way. That is one. Yeah, precisely. Exactly. Yeah.
You haven't learned that, like, the third word.
No. There is no such thing. This is for every location, you come up with this category. All this is doing is a categorical. And remember the parameterization was actually, sorry, somebody said something. Remember the characterization here was product form, conditional product form. So that's why it's L by L. Okay. And what we are going to show is this is just an ELBO lower bound. It's unclear whether this is tight or correct or any such thing at this point. Okay. This is just a lower bound. This is a parameterization. If I get, hopefully today and next class, I will argue that this is indeed tight in a limiting regime. Okay, exactly the same as the flow, the flow using a discrete flow matching viewpoint. You can get the same thing in some limiting thing. The limiting thing is in a limit where at every quote unquote time step, nothing is unmasked and no change happens. Okay, and then with very, very small probability, one of them will be unmasked. Because you see, what I've given is a product distribution. So theoretically at this point, you sample from each one of these things. Okay, you could unmask many of them simultaneously. Okay, and we can see that this is going to be a problem. This also goes back to what Sujay was talking about. Okay, because the characterization is fundamentally not correct. It's not product form. Okay, it's some joint distribution. So, but in this limit of a CTMC, only one will get unmasked with very small probability, and two will get unmasked with probability h square, where h is some time square thing, which is all really, which can be all vanishing. So in that limit, things are correct. Okay. Which is actually analogous to the DDPM, the discrete time step thing, versus the actual flow thing. And there it wasn't about the product form. It was essentially that you're using the conditional expectation to make all decisions, not the actual distribution. So you could argue, if you just use the conditional expectation, why should things be right? It's not an exact analogy, but it's a rough analogy that sort of has a mental model. Okay. All right. So, but at this point, we are left with predicting this. How do you learn this categorical distribution that you want to learn at each time step? Okay. And this is learned. There are two properties. This learned categorical distribution should satisfy two properties. One is what it's called in literature zero masking, meaning it does not have support on the mask because you're actually predicting x theta is a surrogate for predicting what x0 should be. So this is called the zero masking property in literature. The other is something called carryover unmasking, which is if it's already unmasked, then x theta will be a one-hot encoded vector. Meaning it will predict that, it will carry over whatever is unmasked to predict the same unmasked thing. No, I'll show you exactly how that in the loss function, how are we implementing this? We'll see it in a second. While I'm defining two properties right now. This is called x theta has these two properties. How do you force x theta to have this property is what the training is going to be.
Does that mean that once the token is certain, that will follow for the all time?
In the default thing, though there are there are variants, remasking and all that. So as I said, I'm just talking about the most basic one of this thing, which is pure. Once in this setup I'm describing here, once it's unmasked, it remains unmasked. Though that is not the state of the art today. Okay, you'll need to remask once in a while and that has shown to have much more improved performance. Okay, but then all the derivations which I'm going to do will change. So for concreteness, I've just taken one model. Yeah. So now let's derive the training loss for this. Okay, using so one caveat is that I had x and z0. I'd sort of merged these two together. This was lot. So in the latent process, we started from z0 all the way to z1. We could even, but I have sort of, so far I've been talking as to x and z0. The data in the first step is the same thing. It may not be depending on what you want to do. If you want to use this model for certain post-processing, you could introduce x and z0 to be separate. And the loss derivation has that in the derivation, but most of the time my understanding in practice, unless you need that, you just skip that first step. So I'll first describe the training loss and then and then we'll derive this. Okay? The training loss is ignoring the first reconstruction step. It is for every time step in the diffusion, you have some weighted cross entropy loss between the predicted token and the actual token. So this is a one hot thing. This is a distribution, and that's all there is to it. So it's very intuitive what this loss is. But let's actually derive this. The claim is that the negative log likelihood is upper bounded by this particular loss. The proof, so we'll write the proof for the L equal to 1 case. That means just one token. We can the same proof structure generalizes for multiple tokens. You just need to keep track of, use the product form structure, put it in, some sums will all come in. Okay. But we will just write everything out carefully for one token. So let's start with the ELBO lower bound. Remember, when we did VAEs, we studied the ELBO lower bound. It said that the log likelihood can be written as you can always introduce any latent you want and marginalize out this latent. So you can always write the log probability or the log of the marginalize of joint for whatever Z you want. And what we did is we said, okay, we then introduce some forward process, which starting from an X predicted as Z, which could be parameterized. We just simply just multiply the same thing. This is one. Okay? And after some algebra, we got, and Jensen's inequality, we got the ELBO lower bound. Okay? It said that what we want to, this quantity is lower bounded by this ELBO lower bound, or the negative of this quantity, which is what we've written, is bounded by the negative of this, which means the ratio changes. Okay. After some more algebra in the DDPM, I'm not going to repeat all that. The latent Z was not one Z, but we could think of latent as a vector, the various steps of the noising process. And so you had Z0, Z1 over T, Z2 over T up to Z1. These are the latents. And so simplifying that, we got the following, that the ELBO lower bound could be rewritten as the following. It could be it's written as the log of, look at the one step Sorry, I think I've written something wrong. Let me just go back. Apologies. Correct. Okay, it is correct, but I used the wrong intermediate term, and that the ones you could redo the ELBO lower bound as a sum of KLs. That's what that log ratio was. But what I wanted to highlight is that the KL divergence is between the predicted one step back. Okay, this is P theta, xt minus 1 xt, whereas this is the true, not the true one step posterior, but the true posterior with an additional conditioning of the initial token as well. So that's what I mean is it's not this. It is actually this. Okay, it's a different posterior that comes in. So q xt minus 1 comma xt x0 is what we have been dealing with last time, which is I want to figure out what happens at time t minus 1. To do that, I'm going to not just look at given xt, what happens here, given xt and the other full endpoint, what happens. Okay? And p theta is trying to approximate this particular object. That's what the ELBO led to, which is again what motivated us to sort of approximate p theta when we discussed in last class in discrete as well as in DDPM. We didn't try to approximate p theta xt minus 1 given xt by q of xt minus 1 given xt. Instead, we approximated by q of xt minus 1 given xt comma x0. And since we didn't know x0, p theta's parameterization of x, the conditioning of xt became predict x0 based on xt and use the structure of q of xt minus 1 given xt comma x hat of 0. Okay? So I will fix the notes, the main notes in a minute after class. Okay, so in the next step, I have it correct. It is just that inset was not written correctly. Yeah, well, the inset is correct, but it can be further simplified. And I wrote the intermediate expression when I should have written the correct, the final expression. But nevertheless, what we have is the sum of the terms, each one, which is the KL divergence between this Q, we'll call it the inference posterior, and P theta, which is the parameterized thing. The rest of the next 10-15 minutes, we will just get an explicit expression for this part and see what how all these things about carryover masking, all these things come in, and how can we simplify this and actually get just that cross entropy loss. First, so we'll look for a particular I, fix an I, and we're just looking at just this term, log of Q of Zs given Zt comma x divided by P theta of Zs given Ct. We're just looking at this one term. This term, so the ith term in that is what we have written here. The random variables here are Zs and Zt, and they're both drawn from the conditional distribution given x. We can break this up into first in the outer expectation of Zt given Q dot given x, and the inner expectation Z of S given Zt and x. Okay, this is the way we are breaking up this expectation, and the same term here. So first, let's analyze just this inner one. So as far as the inner expectation is concerned, both Zt and x are fixed. Okay. So there's a case-by-case analysis. First, let's in this inner so look at this Zt here. It's fixed because the mask model and x is also given. Zt can take only one of two values. It can either be x itself, or it can be m. Let's make sure you understand that, right? Is that making right? Because I've told you the initial condition, we are looking at time step t, what could happen? It could either remain that thing itself because the pure didn't become masked, which means it's x itself, or at some time before that, it will flip to a mask and it sticks to mask afterward. So there are only two cases to consider here. Zt is m or not equal to m. And when you say not equal to m, here it's equal to x. For a uniform model or anything else, the calculations and all that will change. Okay, I'm just the easiest model. The only two states I need to consider. Okay, in this case, when Zt is not equal to m, meaning Zt equal to x, then the claim is this term is identically zero. Why? Okay, so we are now looking at this is x and this is x, and look. So that means look at what Zs could be. Zs now again would be either m or x. What's the probability it's m given that it was x at the start and x in the future? It's zero, because it cannot, right? It must have, because it did not get masked on both sides of it. It's x, therefore it must be x there as well. So this term goes away. And given that Zt is x and the beginning was x, it must be x. So this probability is 1. Okay. Zs is x, given Zt is x and x. So this is 1. And now the carryover unmasking implies that this also has to be 1. This is the parameterization. Okay. So we will force this to happen by putting we will supervise the loss there to force this to happen, Sujay. So that's what this carryover unmasking is forcing. And therefore, log 1 by 1 is 0. So A is log 1, which is 0. So the A term happens to be 0. Okay. Case 2, Zt is mask. Okay. So we are looking at the inside term here again. So now we are looking at the conditioning of this when Zt is masked. So I'm at x at beginning. It has gotten masked one step after me. The question is whether at time s it is x or m. Okay, these are the two options. So let's write the expression. So it is Zs could be either mask or x. So Zs is m, Zs is x. We just write, these are all discrete, so we're just writing the probabilities out. We are expanding the expectation out into probability times the function with Zs equal to m here and Zs equal to x here. That's all we have done. In this case, now, what do we know here? We know that the parameterization was such that the one-step learned probability is a categorical weight x theta weighted by this. So this is just a distribution, or it's masked with this probability. Whereas the inference inference posterior q is x itself or m, okay, with these probabilities. This is what we have seen. We just discussed a few minutes back. So let's stick all this in here. Okay. So I'm going to shrink this so that we can see various things. Is this font okay, viewable? Okay. So this is this. No, sorry, that is this. Okay. This, because it's equal to mask. So we are just taking the mask probability. You sticking the mask probability again here. For this equal to x, you use this probability. These goes to these things. And for this one is the piece. So this is zs equal to m given zt equal to m. So for m, you get this, you get that there, and you get this there. Okay. I'm just putting these things in. And so let's simplify that. Which means it is, but since the masking, so going back to Constantine's comment, the masking was independent of L. So which means these probabilities cancel. It's okay. Well, even if it depends on L, it would cancel, but it matches the Q. That's really the point, I guess. So this term goes away. And on the other one, that it continues to remain masked. It's weighted by the Q's probability that it continues to remain. Sorry, the other one is when it's decoded to X. It's the Q's probability that's decoded to X, log of that probability. And now look at what the predictor is doing. Okay, it is, let's go back into this categorical. What is the, so let us say that this letter X was the jth element in Q theta, X theta. Remember, X theta is a vector over the vocabulary, right? It's a soft predictor vector. X, which you're conditioned on, is some letter in that thing. So let's say it's a jth one, okay? In which case, then what you need to do is to look at this X theta, extract the jth element of it. That's a probability. And that's what you need to use here. Is it making sense, what I'm saying, or is it a little confusing? Didn't make sense? Okay. Okay, that's what I figured. Let me, because okay. What we want is the probability that you're under your model is predicting that the next one should be X given M. Let us see what that is. Now we know what X is. X is the jth element in X theta. Little x is the word. It is some word. Let us say it's a jth element in the vocabulary is just an integer sequence. So let's say little x equal to 25. Then you need to look at the X theta is the distribution of 50,000 dimensions. So you need to look at the 25th element of X theta, and that would be the probability of this one. Do you agree? But not quite, because it's reweighted. It's reweighted by this. So this probability is equal to this times the 25th element of this. Does it make sense? Yeah. So that's all I've written here. Okay, where select the jth index where j corresponds to x. But x itself is also just one hot in the jth element, it's 1. Which means you can write this as the inner product of x theta zt and x, because this is a selector. Okay, and so A for this case is this term goes away because it's log 1. This term is this part cancels, giving you negative log of this, which is just this inner product, scaled by this. Okay, So if you put these various cases together, the overall term is when zt is not equal to m, as an indicator, times 0, and zt equal to m, you get this. Good. Now, we'll argue that this can be dropped. Okay? Because we will argue that when zt is not equal to m, this itself is 0. So we can come up with an expression without indicators. That's what I want to do next. So when zt is not equal to m, okay, I'm given x. Now carryover unmasking is important. So this is the other place where supervision is required. Okay, when something is unmasked, it remains unmasked, meaning x theta of zt must be equal to x, and therefore x theta of zt inner product with x is 1, or the log of that is 0, which means you can this indicator is not needed because automatically this will become 0 because of carryover unmasking. Okay, and so putting all this together, you basically get that the ith term is alpha t minus alpha s by 1 minus alpha t times the log of this inner product. So that's where the cross entropy loss is coming in, where all those properties are used explicitly to get this form. Yeah, you put these things together to get the ELBO loss. So now hopefully you've seen how the whole pipeline goes through. We have actually it's just use those properties and just calculate things through. And this is exactly the ELBO loss for discrete, for no random reflipping, nothing. It's just a straight through. Once I unmask, I'll stick to unmask. This is what we'll get. Now the question. So we have done the first pass on this on a masked language model. We are going to view this again through a discrete flow model viewpoint for the next half an hour or so. Okay. But before I do that, I want to go back to 2 lectures back and very quickly for the next 10 minutes, think through the whole conditional flow matching. Just look at the highlights of it, because I'm going to, for the discrete flow matching, I'm going to skip various steps and use an analogy to this one. I'm not going to prove things. I'll just refer to the right things. But since we have proved everything here, we'll see the analogy. Yes.
So in the context of
Good. Let's go back here. It's a good question. So all I have talked about here is this model which start from all masks to get an all token. So how do you do question answers, or how do you do any context thing? Okay. One way of doing that is, that's what I had written here. Let's go back here. Okay, so for inference with a prompt or a context. So what you could do is set the state. So you again, the length is always fixed. Okay, you could set the state as some prompt mask. You could initialize with that, and then start your diffusion model with that initial condition, and the mask should become your answer. Okay, but it's not. But that's not what the model has been trained for. So you need to do SFT, or you need to do instruction fine tuning or this kind of a thing.
I did see that those answer is attending to the question in diffusion formulation.
Why? It's full cross attention. It's bidirectional cross attention. Maybe I didn't understand your question.
But in my understanding, not regressive. So every token will attend to the every prior token.
Yes.
To get the context.
Fine. Here the mask will attend to all the prior and all the future.
This happens the diffusion mask diffusion cases.
Yes. If you remember, what is the fundamental pipeline? It's bidirectional attention. Okay, and that's remember, or in the, this is a picture. In the math, where is that happening? Okay, in the math, it's happening here. Let's look at the parameterization of this. Yes, here. X, you're decoding the Lth token based on ZT, not ZTL. That's the crucial thing, which means, okay, so that's the thing. That's why I said it's conditionally independent, each one, condition on the entire sequence. So be careful where an L is. That's actually very important. There is no L down there. So I think that's what you are looking. Okay, this clarifies what's happening? Okay, so, all right. So now you see how this model works. Now let's go back to the continuous diffusion, just to summarize how the flow, how we thought about it through flow matching, and then come back and think about diffusion through flow matching next. Okay. So this was the summary we did 2 lectures back. I'll just very quickly just summarize the highlights of what we did then. Okay. So we said x0 was initialized with some distribution p0, say Gaussian or something like that. X1 was a sample from the data distribution. Okay, and then we want to learn a velocity field so that you feed in that sample x0 and run this ODE. Then you're going to get at x1 this continuous time, continuous state space in this setting here. Okay, you will at x1 you will get a sample from q star. Okay, so we are creating a coupling between these two distributions, between p0 and q star, and this coupling takes a sample from this and transports it to a sample on the other side. Good. This is the illustration. This is a random variable. This is a deterministic velocity field. It's pushing it from here to here, which means there's an induced PMF at each point and PDF in this case, induced density at every point in time. Initially, this one here was Gaussian, and as it moves, it becomes Q star. Okay, that's the density evolution. And this velocity field and densities were intimately related by the continuity equation. Okay, which said that the derivative of the density is negative of the divergence of the probability flux. UTPT was a probability flux, and that's basically that tells you these two are related. So then, what we did then was the following. We said we want a quote unquote straight line sample. We start with a target of a straight line sample path, and we then came up with a conditional density of xt given x1. So if I anchor it on the other endpoint, if I say that at time equal to 1, this is the value, okay, that's the conditioning. Then what happens? With this condition, you'll get a conditional density and a conditional velocity field. Okay, but these two are again related by the continuity equation. Because your condition on this world, the world is just x1. It's a new probability space. In that space, you can write the density. You can write the continuity equation, and then the unconditional and all these conditionals are related using the total probability theorem. And if you put these, so now you can go to the algebra, and what you're going to get is the following: that the unconditional velocity field can be written as a particular expectation of the conditional vector fields. So this whole point, this pipeline was useful for the following. I'm interested in finding a conditional velocity field. To do that, we will first define the associated conditional density. I want the unconditional velocity field. So we will define the unconditional density, but and we know the relation between that because of the continuity equation. Then we will define the conditional density. The conditional density is related to the unconditional density through total probability theorem. The conditional density is also related to the conditional velocity field through the continuity equation. And the conditional velocity field, therefore, is related to the unconditional velocity field through this expression. What's the purpose of all these gymnastics? The reason is, of all these, so to train, you need to start with something you need to know, one of these quantities. There is a closed form expression for the conditional velocity field. That was the whole point of this business. Meaning, we also saw that if you want this straight line path, okay, this is a trajectory, and now I'm conditioning on x1, then the conditional velocity field is very easy. There's a closed form expression. It's just a time scale. If I'm at any point, move towards x1, okay, with just appropriate time scaling. We derived that last time. So once you have this closed form expression of the conditional velocity field, we are in business, because now we can write the unconditional velocity field through all the expressions we said as using this one. Okay, so we have moved to that one. Good. We have got the unconditional velocity field. Now, once you have this, now the question is, how do you train a model to do all this stuff? So I need to learn. Remember, what I need to do is to learn an unconditional velocity field. So, meaning ut theta should approximate u theta, ut. Okay. The whole problem was I didn't know this. I knew I have only an expression. So to do a loss function on these two, if we didn't have an expression on this, we couldn't do anything. Now we have an expression for the unconditional, for the conditional version of this. The next thing we showed is the following. Look at the loss function. This is the true unconditional velocity field, and this is what you're trying to learn. If you had an expression for this, then potentially you could do gradient descent, whatever, and learn this and optimize for this. We don't have an expression for this yet. We have a sort of expression, but it's still not explicit, meaning there is some expectation in there. Okay. What we do have really an expression for is only this. Okay. So the next step in this process was the following. Look at this conditional flow matching objective, okay, which is try to approximate the unconditional field by the conditional. This seems somewhat bizarre at first sight, because previously we said we want to learn this. We want to approximate ut theta by ut, which makes sense. But this one, it's a conditional version. But we said this is okay. The key result we proved is even though the losses are different, the gradient with respect to theta for both the same. So if we train for this loss and get a model, that model would be the right model for this loss as well. That was the key part of this pipeline. Okay? So that's why we went through all these steps. So therefore, now you can train with this conditionings, with this conditional velocity field, and get a model. Okay? This is the whole flow story. Let us see what else I want to highlight from this pipeline. Okay, yeah, and this can be further simplified, but this is immaterial to our story right now. This could be simplified further into sort of a loss which has a different, very nice interpretation, right? You want to interpolate between these two, and between x1 and x0, you don't know what it is, so try to do it on an average. That's another way of thinking about it. And these two ways were equivalent. But for the story I'm trying to tell today, I don't need this. I just wanted to get the various pieces of what we looked at so far. Constantine? Okay, so I'm just summarizing this story. To keep in mind, because I'm not going to revisit this once more in this class, this also has a connection to the stochastic interpretation. This is what we did when we said that you can get an SDE version of these kinds of things. So they're all equivalent to each other. But for the purpose of today's thing, I just want the pure flow view. To do that, go to the conditional flows, get a closed form expression for the conditional flows, then approximate the unconditional flow using this using the conditional flows, and it all works because the gradients are the same. Okay, all right. Now let's do this for discrete. So all this was continuous time, continuous state space. We want to do something like this for discrete state space, continuous time. And think of this discrete, so discrete state space is the vocabulary space. It's continuous time. Think of this as the limit of what we studied previously, where the number of steps t goes to infinity. Okay, so we are taking many, many, many steps in this process. That's sort of the mental model. I'm going to follow from Lippmann et al.'s paper. This is a really nice tutorial, so I'm going to continue following from that in terms of notation. But there are some parts where actually these calculations are done for the mass diffusion model and for the uniform model. I personally prefer this one. It's cleaner. It's Shaw et al. It's the appendix D of this thing is actually very clean. So if you want to understand exactly the calculation, because I don't have time to do the detailed calculation, it's worthwhile to read that appendix. Okay. So let's understand a continuous time Markov chain model. So state space is it's discrete. There are L tokens. Each token is from the vocabulary 1 to k. Okay. So any state is of the form x1, x2 up to x7. Okay. So it's just a sequence of integers. Okay. That's all this is. And the CTMC model, I will describe it in terms of small discrete times. There's a better way of describing this through Poisson jumps and all that stuff. I'm going to ignore all that and sort of give a working definition of CTMCs. which is the following. If I know that at time t, I'm in state x. In fact, this is all finite state. It is not even countable state CTMCs. We are all doing everything finite state here. Huh?
Yeah.
It is, but just for concreteness, okay? It is the same, but you need to handle more technicalities, non-explosivity. There are all sorts of other things we need to worry about, right? Here I can soup and max, and I don't need to worry about any of those kinds of things. Then at time t plus h, I'm in state y with the following probability. That is, the probability at time t plus h I'm in y, given at time t I'm in x, is this delta yx, which is 1 if y equal to x and 0 otherwise, plus h times some ut of yx plus little of h. Okay. So ut is the rate of going from x to y. So that's normally when you think of pij's, you go from I to j. That's why I want to highlight here is going from x to y, and I'm using the notation from these papers. This is sort of different from the way I think about CTMCs because the vector is going the other way, but we will use this because that's where all these notes are used. Okay. So graphically, if you've got any state x, so this is the rate of going from x to y1, x2, if you're on y2, this is the rate of going from x to, I keep saying things wrong. This is the rate of going from y1 to x, this is the rate of going from y2 to x, and similarly from x to y3, this is the rate of going from x to y3. And what's the conservation? Well, if y is not equal to x, this is non-negative. If y equal to x, this will be the sum of all the other terms, meaning the sum over all ut y comma x equal to 0 over all y. Okay, y could include x itself. Okay, why is that? Look at this expression. What this is saying is because this probability should sum up to 1. For any x over sum over all y, it should sum to 1, which means when y equal to x, this is some negative quantity. Okay, this is 1 so it's this is sort of 1 minus some h times some quantity. That's what the probability is. And for every other state, this is 0. You'll go out. So all this is saying is this velocity is when time is chosen to be small enough, with very high probability, I'll continue to remain where in the discrete time chain, discretized time step system. With very high probability, I'll stay where I am. With when the rest of whatever that remaining probability is distributed to various states depending on this velocity. That's it. And velocity times h is the probability itself of being in that state. Constantine, is it okay? Yeah. I know I'm making a big deal. I'm just wanting to get all the notation sorted out. Okay. I know everybody in this room knows this, but it's just worthwhile to sort of talk about it. The second thing is about divergence. Okay. So let's recap. Going back to your other classes, what is flux? So rho is a flux. Flux is essentially the rate of flow of a vector field through a surface. Okay. So what is divergence then? Divergence is a measure of accumulation of a flux at a point, okay? Which is why we got the continuity equation and the conservation of mass, which is del T of Pt was equal to minus grad del dot rho. Basically, which is saying that look at this, look at some x and some small ball. Look at there's flux coming in and flux going out. And divergence is this measure of accumulation. In the continuous limit, it was nothing but del rho by del xi, summation over all dimensions. In physics, it's only over 3 dimensions. Rho is flux.
Through some surface you haven't.
Yes, through, in this case, it's a small ball or infinitesimal ball about x. This is a continuous time system. In the continuous thing. Yeah. No, rho x. That's yeah. So now, and this led to the continuity equation. We basically, which is a conservation of mass. There's a probability flux which was going through. That's how we derive this. And so if this is not 0, then the probability is leaking out of this. Actually, I guess I have a sign wrong, right? Yeah, it should be negative. Is this correct? Continuity equation, is my sign correct or wrong? Del. accumulation is a negative.
That's right.
Yeah. Yes, this is correct. I got a sign wrong. So there's a negative sign there. Okay. So this is what was the discrete viewpoint of this flux thing. Let's do this in CTMC and see what divergence means for continuous time. For discrete vocabulary, continuous time. Okay. So I've got a state X. The incoming probability flux is summation PT UT. Okay, from Y, so it's discrete. Now it's not, I don't need to integrate, I want to check over every possible state. From Y2, the probability flux coming in is PT UT from Y2 to X. Similarly, from Y1, it is PT Y1 UT of XY1. So these are all the incoming fluxes. Then outgoing fluxes, PT of X, because we are at X, UT from X to Y4, and so on. You've got incoming and outgoing probability fluxes. And so discrete continuity equation is, yeah, the negative is already here. Okay, good. I haven't. So the incoming probability flux is the sum over all Y not equal to X, UT of from Y to X, PT of Y. The outgoing flux from X is sum over all Y not equal to X of UT from X to Y times PT of X. Of course, you could have pulled this PT of X outside because it's not this sum, but doesn't matter. We have just written it this way so that it looks consistent. Is this good so far? Okay. And now the sign is correct here because the incoming minus outgoing. So the discrete continuity equation, just like the continuous version, is nothing but del P by del T is incoming flux minus outgoing flux. Okay. So you have the continuity equation exactly in analogy to what we did in continuous state space. You can do something very similar with discrete divergence defined this way. So we can define this difference as the discrete divergence of UTPT. Okay. So it looks mathematically now, it looks identical to the continuous thing. And so in analogy, we will do all the calculations we did with continuous flow models, but with this notion of divergence. And essentially that will give you whatever we did with the CFM, continuous flow matching, conditional flow matching, we'll get similar story here. Okay. To see, so all this is intuition. I just said this is a continuity equation. Why is this true? Okay. One way to see this is the following. Okay. Let's write this again. Del P by del T is sum of incoming flux minus outgoing flux. Okay. Now, remember the velocity fields. It was such that at any particular x, the sum of velocity fields must be equal to 0. And this came from because so that the one-step probability, the h tiny step probability should sum to 1. That's where this came from. Okay, and so which means that UTXX is this negative of this sum over all y not equal to x UTYX. Just from that. So now look at this outgoing flux. PT of x, this is a summation over y. PT of x can be pulled out. Okay, so you get PT of x times this summation. This summation is nothing but negative UTXX. Okay, and this negative multiplies to give a positive. And so you can write PT of del PT by del T is summation over all y, not y equal no infla of UTPT. And this is the backward equation for CTMCs. So continuity equation is essentially the backward equation. Okay. So it's just a way of rewriting it. Okay. You may not have seen this in a Markov chain class. So when I, for example, teach random processes, I didn't teach this stuff. So I thought this is worthwhile to actually do this calculation. You can see this connection. Okay. Okay. So where we are is now we can start studying. Now we have a notion of density evolution in a discrete state space. I can start from a discrete vocabulary, finite vocabulary with token, and talk about what its density is and how it's going to flow, the divergence. We can write all these equations, this flow equations. And so we can think about everything in this flow space. Okay. So same, we can now talk about the velocity field of a discrete language, of a diffusion language model or a discrete language with discrete vocabulary exactly through this language now. because again, we have a PT, UT, and all that stuff. Their meaning it's closely related to what we saw previously, but the operations are somewhat different. We talked about what these operations mean, right? Okay. So the first result is that it's intuitively very clear that this should be true. If PT and UT satisfies this continuity equation we just saw previously, then UT generates PT. Okay, meaning we can choose that if you implement that UT flow and at every time, then the density evolution you're going to get is this PT satisfying the continuity equation. Okay. Again, I'm not going to do any proofs for this one. The proof will use the same thing, Bayes rule, total probability. We did this kind of a proof previously. It is enough. You need to do a little bit more work. As I said, we are almost there. We need to do a little bit more. That's all. Okay. There's a second thing that's actually useful for discrete flows. Discrete vocabulary continuous flows, which is the following. Suppose a velocity field is divergence free, meaning you find a V tilde such that PTVT summation over all x is 0. Okay. Then you see that the solution here need not be unique. I can add because it's all I could add a diverge 0 quantity to it, and I can still get the continuity equation said del PT is minus divergence of UTPT. I could always add a 0 to it, and that 0 happens to be through a velocity field. So, which means if you have if you have found a velocity field, you can engineer it with divergence-free velocity fields and still get the same density evolution, which is useful for implementations. Okay, so you got some velocity field which is complicated, but if you can make it simpler by adding a some 0 term to it and still get the same thing.
Like it's just like going in circles, like what is
yeah. Yeah, what is the kernel of a divergence-free field? 0, right? That's one. So again, you have to go through this. Yeah, I'm just saying this is useful. It is used for parameterizations. This one, you got some U that you get, okay, and I want to make it look nicer. I want to implement it differently. If you find a V tilde which satisfies this property, you can change your parameterizations, and that's what they do in some example. I'm not going to go through the details. I'm just giving you a high-level story here, since Okay, so now this is the CTMC background through sort of a divergence and a continuity equation viewpoint. Okay, so now let's look at discrete flow matching. Again, we want to couple between a noise distribution and a data distribution. The data distribution is a sequence of tokens with some joint distribution Q. The noise distribution is what you choose. In this note, we will mostly stick to uniform. Okay, the same kind of thing has been done for mask as well, which is what I pointed out to that reference 7 appendix D. You can read it for seeing how these calculations flow through there. Okay, so the uniform noising model is the following: that you start with a uniform distribution over the vocabulary. That is your noise distribution. Okay, as opposed to having a special token called a mask. Okay, and so okay. We have a sequence of tokens. The reverse processed is initialized from this noise distribution, which is IAD, a CTMC. Now you do this baby step CTMC with H going to 0, essentially. And so you run this backwards, and you're going to get the data distribution. What we want to argue is we'll come up with a parameterization so that it actually transport from the noise distribution to the data distribution, which means effectively that this parameterization in the limit is correct, because we are actually transporting from the noise distribution to the data distribution. So this is again true only in the limit where the step size goes to 0, which means that with high enough probability, nothing happens in most steps. With small probability, one token gets decoded. And with 8 square, even much smaller probability, multiple gets this thing decoded, which is the error event essentially, which anyway which will sort of vanish when we take the limit h goes to 0 limit, and so the flow is correct. So what we are going to derive is the density evolution and the velocity flow for this transport. Okay. So one more point, maybe this is done in literature, but I couldn't find it. Maybe someone knows this. It seems we can take this flow model and talk about as a number of steps in a discrete language model. What is the error in Dino? What is the error? How far away are you from the ground truth distribution? Okay, I don't think that, just like what we did for the continuous case, right? We did the IMMSE proof, we did the Gisanoff proof, and all that stuff. So things should work out here, and you should be able to get explicit. I mean, the same theory should hold, but you should be able to parameterize things given this language, masking, all just like what we did for the ELBO. When you specialize, I'm sure something will pop out, and we should be able to get something close form. Maybe somebody has. I just don't know. But given this, what we have seen so far, it seems like it's an exercise to be done. If you know that there is a paper that has already done it, let me know. But I couldn't. I just don't know. But there might. So now let's get to discrete flow matching. Okay. So we start with the noise distribution. X is in P. P could be either all mask, or it could be uniform over vocabulary, IAD across tokens. The data distribution is there. And then we can take X0, X1 as an independent coupling, meaning the joint distribution of the two endpoints could be simply product form of pick a noise sample at random, pick a data sample at data sequence of tokens at random, and couple between those two. Though there are other couplings you could do the same. For example, X0 could be the token sequence in French. The X1 could be the token sequence in English. And you could find a path to couple between those. Okay, if it's exactly the same. But this, yeah, okay, it's an L-length token. And that means the graphical model underlying this is there's something called content, which is this latent variable, which leads to the two X0 and X1. And you don't see the latent. You just see these two. So there's X0 and X1 has some joint distribution, which is condition independent given this content. But the joint distribution of these two is marginalized over all possible content. So it's a mixture distribution. Therefore, it's not conditional. And then you could do what we are doing here exactly for that. But for what I'm giving you is just a sketch of this story here for the discrete so that you understand the big picture and you can sort of drill down into these papers. Okay, so how would you do this? First, you construct a probability path PT of X along with a velocity field ut yx. So here the velocity field is parameterized by two things, right? Previously it was just a vector. Here ut yx is a jump. It's a ut yx is a scalar. Okay, it's telling the velocity from x to y. Okay, so that's why there's always two parameters. There are 2 points, beginning and end point, because in a discrete state space. Unlike in the continuous where I could deal with gradients and all that automatically, here I need to talk about from here to there. Okay, it's okay. All right. And so we need to transport from X0 to X1. So we will again define a conditioning. Here the conditioning is going to be X0 comma X1. And that's what we are going to call Z throughout. If you read the papers, it's left for many arbitrary Z's. Z can be way more general. I've just sort of taken the simplest version of that and put it here so that everything we are discussing here is very concrete. But the setup is more general than this. Okay. So you can look at the conditional PMF and the conditional velocity fields given the Z. Again, why we want to do this is because when defining a loss function, dealing with U itself is going to be tricky, but these conditional ones are going to be much easier to deal with. And for very similar reasons to why in the discrete language model, it made it easier. Grounding it on both endpoints gives you much better understanding of what it could be in the middle. You can get closed form expressions of what is in the middle. And so lots of closed form expressions can happen because of this. Okay. So for Z is x0, x1, then total probability theorem, the marginal density at marginal PMF at time t is the conditional times the marginal of Z. And we can write the unconditional velocity field as the expectation of the conditional velocity field, condition on xt equals, summation over Z. Yeah, correct. This expectation, okay, I should write this carefully because I've written xt equal to x. It's okay, it's correct. This x, sorry. Yeah, so it's appropriate expectation. Proof, similar to, I'm not going to prove any of these things. So today I'm just telling you, there's like, you can believe that this kind of a thing should be true. That's so this proof we proved this version of it in when we did conditional flow matching. The essentially the same that proof used Bayes theorem and the various continuity equations for conditional and conditioning went back and forth with it. Again, here we have the same thing. We have Bayes for discrete. We now have the continuity equation. We have this for discrete. So essentially you do exactly the same proof with the new continuity equations. It happens. Okay. Fine. So the point of all this is, if you want to say there's a particular velocity field that generates PT, well, instead you can work with these conditional velocity fields to generate PT of x, use total probability theorem to go between this and this, meaning then this can go to that. Okay, so that's basically what this allows. Now let's get to parameterization. So far, we had left PT to be anything you want. Now we are going to impose product form structure. Okay, in this. So PT given Z of x given Z. Okay, PT is at time t, xt. We are going to impose that it's product form across components, condition independent, but condition on the entire Z. So this addresses the question you're talking about. But the local one step is still product form. You see that this is, if you let this run all the time, you're going to get into trouble because you'll get tokens that are independent. So you need to update all the time. In a discrete time, this will break if you take big steps. But in the continuous time limit, as I said, multiple tokens being nothing, the probabilities, okay, if you do, the probabilities of all these error terms, joint decodings, all head square terms, so they will all vanish, essentially. So this parameterization is okay. But of course, this leads to slow decoding. This is again what Sujay's point was last week when we talked about things and in this talk as well. So again, Z is x0, x1. We'll further parameterize PT using a straight line path or a time interpolation. We will say that PT, so given Z, remember, is x0, x1, the two endpoints. We're going to put a delta function at each endpoint and simply interpolate between those two. If kt equal to t, then there's just a straight line interpolation in probability space. Because time is between 0 and 1, there's a convex mixture. But kt could be any other thing, could do nonlinear warping or whatever in this thing. So you're just finding a path to move from this two delta functions, essentially, from this sample to this. That's the density. That is the conditional density evolution. So this is the easy thing we can work with. So now let's start from this. If you start from this, then you can write the conditional density evolution through the continuity equation, which we just derived. Okay, so if you do this, then you can actually get an expression for the conditional velocity fields, which is again a closed form expression. Okay, given this. Okay. Exactly. This is velocity field for x0 to x1. So from data to noise. But because it's all flow, it doesn't matter. Just change the sign and you'll get the other one. Because it's a flow model. We are conditioning on x0 and x1. We have a path that goes. We are conditioning on both endpoints. This is a noising process. But
But this is not for learning.
Exactly. This is all okay because this is not for learning. We are setting up all this, and finally we will do learning exactly like what we did before. We will say we'll try to guess this thing. We'll parameterize it appropriately. Exactly. The point is, for setting all these things up, we need close. So for learning, you need what you're learning with against. And so all this is giving you what the expression should be for your loss function. That's all is happening here. So this is a closed form expression for the conditional velocity field. And now, if you go through this parameterization, because this is all, we had this and this. We had this as product form, this in this interpolated form. You can argue that this leads to a factored velocity field, meaning the utyx can be it's a sum of it's in a factored form. You can write this thing. Okay, so which means that, or equivalently, it gives you the parameterization of the forward sampling process. This is a forward is for the ith token, ith noising. Look at the joint vector. Okay, the entire joint vector. It's if yi equal to xi, it's 1 plus some h times the factored velocity. Okay, so the key point to note is there are two design choices here. Z is x0 and x1. That's this thing, and PT condition on Z is product form plus this interpolation. Okay, these things can be generalized beyond all this. But for scalable implementation, these choices are important. So this goes back to a side conversation again we had after class last time. What if you say, oh, I don't want to just jump one, I want to learn some mapping from any state to any other state. Then you can't just learn product form, you need to learn some joint thing. And so it's much harder learning problem. You can write all that out, but the sample complexity of learning, that just blows up. So now how do you train this? You train this. So previously we trained it using squared loss for the conditional flow matching. But at that point, we made the statement that, yeah, that theory all works for any Bregman loss. So a different Bregman divergence is a KL divergence. And essentially, that's what is going to be used here, okay, to get things going. Specifically, I have to have few minutes. Okay, I should be able to finish. Define the following types of velocity objects, which is non-negative. Its subscript is x. It's non-negative in all coordinates except x. And at x, it is the negative of the sum of the other coordinates. It's sort of the conservative. It is the u, essentially. That's what omega x is. Okay. And then you can define a convex function phi x and an associated Bregman divergence over these kinds of vectors. And then you can write the discrete flow matching loss as minimizing a divergence, such a divergence between ut and ut theta. This is what you'd like to do. Again, this is an analogy to what we did is conditional flow matching there. And we can do the conditional discrete flow matching loss as between ut given z and ut theta. Okay. This side is there's no z, there's z. Exactly an analogy to the story we saw 10 minutes back. Okay. And not surprisingly, these two have the same property. Okay. Therefore, you can use this to train for this. And this one we saw has a closed form expression. We went through this thing here. We saw that okay, because of the straight line interpolation, because both endpoints are fixed, and you're in business. So now what I haven't written out is, so we have this. How do you go from this to the cross entropy loss we saw last time for masked or for uniform? Just read the appendix D in 7, which works. Start from this, go to the calculations, you're going to get that. Okay. Some of the steps involved is the following. Log 1 plus x is approximately x for x small. That's basically key in running some of these calculations. Okay. Other than that, it's pretty much the same algebra. This is only approximation. And this really uses the form that log 1 plus x, the x is of the form u times h. And so for small h, you can get this, and then you're going to get the same kind of calculations. Okay. So you have now seen the sort of the discrete flow matching view of the same kind of process. You can look at it from an ELBO, from a flow matching, but finally, from an implementation point of view for this one, if it's scalable, it both leads to the same MDLM type algorithms. Okay. Yeah, I'll stop here. Next class we'll finish up. Thank you.